In the final section of our chapter on metric spaces, we are going to discuss compact subsets of metric spaces. So we are discussing compactness here. Just a recall from Math 1, at least in my course, and I think if you took it the year before, you should have seen the same characterization. We call subsets of the complex numbers compact if they are closed and bounded. So by definition, a subset of C was compact if it's closed and bounded. It turns out that this characterization can be generalized to Rn, so to finite dimensional vector spaces essentially, but to our most important metric space, Rn with a Euclidean metric. But we shall discuss compactness in a more general framework. Namely, we introduce a definition which is valid for all metric spaces and which is where we see later on that this characterization is fine in Rn. But for arbitrary metric spaces, which are needed in several places in mathematics, it's taking quite more effort. So at this point, I really want to discuss things in detail. If you shouldn't get some of the details upon first sight, because it's very abstract now, don't be discouraged. This is, for what we're doing in this course, is probably enough very likely be enough for what's to come, that you understand compactness in Rn. And the abstract way, it's just good to keep this in the back of your mind, because at some point you will probably need this, maybe in Math 3. But this is the general description for metric spaces. So without further ado, let me just introduce the notion of compactness. Of course, I could say that subsets of metric spaces are compact if they are closed and bounded. These notions we have generalized to metric spaces. But it turns out this notion is not the right one we're using. So for example, we're searching for, because compactness in this setting here had the advantage, so we had seen some results about compact subsets, namely continuous functions on compact subsets are uniformly continuous, and what was also very important, continuous functions on compact subsets have a minimum and a maximum. So real functions have a minimum and a maximum. So this is what we want to generalize, and this is what we would like to obtain as well, because we want to do calculus, we want to study functions, we want to study their behavior, and later on we will also search for maxima and minima of functions. So we want a notion of compactness which ensures these properties. And it turns out just saying closed and bounded does not, and since the examples where it does not are quite complicated metric spaces, I will refrain from going into detail, but I will also give you later an example of a closed and bounded subset which is not compact in the sense that I'm going to introduce next. Okay, enough talking. Let us start directly with the definition. 1164. So we are in an arbitrary metric space. And assume we have an arbitrary subset A of X. First of all, a family of open sets. A family UI I in I, so where I is some index set, so it doesn't matter if it's infinite or not or something, is a set such that UI is open in X, so it's a subset of X and it's an open subset of X for each I in I. Okay, a family of open sets is called an open cover of A if A is covered by these sets, meaning A is a subset of the union of all I and I UI. Okay, for example, if we have some subset A, which I don't know, might be a rectangle in R2 or something, so just for example, then we have, let's assume we have some family of open sets, so assume we have all balls of radius, of a fixed radius r, let's say. So, and this would mean we have all kinds of balls that we can take around every point. And so we can cover this here, of course, by just taking enough balls. It would be part of the union, we just need enough balls for this. Oops, let's assume the radius is fixed, but this doesn't really matter. So this would be kind of an example of an open cover. There might be way too many sets, for example, so we can, so that some are actually not really necessary, but the union of all these sets really contains everything. So it's covering this set. Now, the general notion of compactness is now defined in terms of these open covers. Namely, we say that A is compact in X if every open cover of this set of A it has or admits a so-called finite subcover, and this just means we can take, if we have an arbitrary open cover of our set, we can always cover A by just taking finitely many of them. So we can just drop many of them. It suffices to take finitely many of these. So there exists a finite subset, which I call J. So this is finite. This is important here, such that A is in the union over all sets with index in this finite set J. So let's say of all J in capital J, Uj. So for every possibility of covering such a set somehow by open subsets, we can always find finitely many. And an example would be this here, because it's not hard to recognize. So I have this rectangle, for example, in R2, and let's say I take all balls of a fixed radius. And since this is kind of this rectangle isn't that big, so it's just some simple rectangle, I can always take finitely many as I did in here. So I can pick finitely many balls to cover this. Of course, if we had, instead of imagine in R2, if we didn't have a rectangle but an infinite strip, for example, so which turns out to infinity, this one can't be covered by finitely many balls of a fixed radius. So in that sense, an infinite strip, so kind of a product of an interval with R, which would be an infinite strip in R2, this would not be compact, because you can't cover this by finitely many balls of fixed radius, for example. And this is, of course, something with, so this has to take place for all open covers. So as you can probably imagine, it's really hard in general to use this definition to show that the set is compact, because kind of all open covers, okay, this is just an insane amount of possibilities, and we can never really guarantee we found everyone. So this is a definition which is kind of theoretically interesting, because this is kind of really useful to prove stuff and to do things, but it turns out to show that something is compact, that some subset is some set is compact. One will mostly use other techniques and not really directly work with the definition, and we will later on learn about other characterizations of continuity which are much more useful in that regard. Instead of giving you an example of a compact set by this description, I will give you an example of a non-compact set. One of them I've already discussed. Let's just, I just summarize this. So this is the one I just had in mind, this infinite strip. So let's say S defined by R times 0, 1 as a subset of R2. So this would be, so we just in the Y component we have the interval 0 to 1, and so everything which has these Y components, and so this strip here in between those two. So this strip here, then we get an open cover, namely by just taking all balls of, say, radius 1, for example, around X, and now indexed by all X in R2. So, of course, with the Euclidean metric, if we take all of these balls, this is an open cover, obviously, of S. So to really prove this, S is a subset of the union over all X in S. So far, this can be infinite, so let's take all X in S, be 1 of X. So this is a very, not very subtle way of covering this. And this is, of course, we can also just simply replace this by all X in R2. So of course the strip is contained in this, because everything is contained in this extremely big union. But we cannot find an open subcover, so without a finite subcover of S. Okay. Second example, similar way, but a bit more general. Consider a normed vector space. As always, we view it as a metric space with respect to the distance function induced by the norm. Now, V itself, of course, we can take any subset of V, so we can also take V itself, then V is not compact in V. Okay, so why is that? Let me argue here, because here I haven't proven technically that there is no finite subcover, just intuitively for you. But this can be also proven in this general setting, that we take that the subspace, that V itself is not compact in V. Namely, we consider again a cover without an open subcover. Namely, consider the set of all balls around the point 0, the origin. And now this time we take balls of all possible radii. So this is open balls which get bigger and bigger and bigger and bigger. So of course, if we just take the union of all of these balls, so if we take all possible radii becoming infinitely big, we of course get everything. So this here is V. So this is an open cover of V. This is an open cover of V. And now let's do the formal proof that it does not have a finite subcover. So if it had a finite subcover, so there we have finitely many. So let's say we have B R1 around 0, B R2 for just some finitely many numbers R1, R2 to some B Rm around 0. But then these have of course the simple property that if I take a smaller ball, it will always be contained in the larger ball. So if I take the largest of these radii, everything will be contained in that particular ball. So if it had a finite subcover, then with R defined to be the maximum of these radii, so R1 to Rm, we get that V is a subset of the union I from 1 to M, B, Ri around 0. So as I said, this is all contained in the biggest ball, so this would just be the ball of radius R around 0. So V itself, which is a big vector space which extends very big, would be contained in the bounded ball here. This doesn't make any sense, and just let me give you a formal proof. So this is a contradiction. If I take an arbitrary vector from V without 0, then if I just take R divided by the norm of V times V. This is just rescaling the vector. So if I take this, the norm of this vector here, this is just by norm properties, this has norm R. So this is a vector, of course it's a vector in V. And it's not, because this has norm R, it is not contained anymore in this open ball of radius R, because everything in there has norm smaller than R. So this is in V without Br of 0, and so V cannot be contained in this ball. This makes no sense. So V is not compact, since we found an open cover which does not admit a finite subcover of the space. Okay, so far so good. Another bit more theoretical source for compact sets is the following. So let me give you this as a theorem, because that's quite general. Assume we have an arbitrary metric space. Assume we have a sequence in X which is convergent. And assume, or let's now put A to be the limit n to infinity xn. So this is also a point in X. Then, if we consider the whole sequence, but this time seen as a set of elements, so just the set of the different components of the different elements of the sequence, K defined by the set containing all of the xn. And if we unite this with the limit point, so if we just add the limit point to this, then this is compact in X. Okay, and to see this, we basically just need to apply the definition of convergence, and it's really not that difficult, so let's do it. So, we start with an arbitrary open cover. Okay, so this is an open cover of the set K. Since the limit point is in K, we have some particular set from this open cover which contains the limit point, so that I0 be the particular index such that, or a particular index, it could be more than one, that I0 in I with A in UI0. Okay, so UI0 is an open set, this is an open cover, so UI0 is open in X. So there exists an epsilon ball around the limit such that B epsilon around A is completely contained in UI0. Okay, this ball is in there, but by convergence of the sequence against A, this means that for this particular ball, if we think about convergence, formulating this with balls, by convergence there exists some n0 in n such that all elements of the sequence from n0 on are epsilon close to A, or in other words contained in this epsilon ball. So there exists an n0 in n such that xn is in B epsilon A and thus in UI0 for all n bigger than or equal to n0. So all of these infinitely many terms of the sequence can be covered by this one element of the open cover I0, and all that's left to do is to cover the remaining ones, which are finitely many, and this is the key here. So for all j in all those elements of the sequence before, so from index 1 to up to n0 minus 1, that ij be an index such that the corresponding element xj is contained in uij. Okay, so this is what we have. Then it follows that k, since A is contained in UI0 and all these are contained in UI0 and all the other ones that are just left to cover are covered by these. So K is a subset of UI1 united with UI2 and so on to UI n0 minus 1. Now we've covered the first n0 minus 1 and now we cover the rest by just adding UI0. This is a finite subcover. So this is a finite subcover. And since we started with an arbitrary open cover and just argued abstractly with the sets, this shows that K is compact. Okay. Now, this is now a class of examples, and I told you we want to see alternative characterizations of compactness and to characterize it differently. And one of the most important ones will follow in the next theorem, where we see that compactness can also be defined in terms of sequences instead of open covers, which we shall see after I erase. The following theorem we will only prove in parts, namely we will see an equivalence of two statements and I will only prove one implication since the other is technically quite intricate and not that important for you to know all the details, so it will be contained in the lecture notes and it's probably also easier to read up than to listen to the proof when I'm doing this here. So let's characterize compactness by sequences. Theorem 1167. Consider a metric space XD and consider a subset K of X. Then, and now can use again my abbreviation, the following statements are equivalent. 1, K is compact. 2, now this is a beautiful characterization. Every sequence in K has a subsequence that converges. In K. Every sequence. So this is probably a simpler characterization, and this is also called sequential continuity, not sequential continuity, sequential compactness. So there is a more, I've said before that there is this more general framework of topological spaces we're not discussing here. There, these two are not equivalent, but in the realm of metric spaces, we can really say this compactness by open covers is the same as the sequential compactness argument. So every sequence has a subsequence converging in K. Now, before we can prove this, we need one technical lemma we need to establish. So I will only prove the implication for one implies two, the other one will be in the lecture notes. And the lemma that we need for this is just a little, very basic thing about sequences. Oh, and by the way, subsequence, I haven't defined this explicitly here, I've defined this in the last semester. I hope you all know what a subsequence is, because otherwise you find it in the lecture notes, I've defined subsequences for sequences in arbitrary sets. So just, yeah, taking a part of the indices and taking a part of the sequence there, that's the idea. So please read up if you don't know what a subsequence is, please stop at this point, read up, and then go on. Okay, but the lemma. So, a very elementary thing. We have a metric space XD again. Metric space. Now, assume we have a sequence in X. And assume we have some point A in X. And the idea is, if every epsilon ball, if B epsilon of A, every epsilon ball around A, so we don't know what Xn does, but if every epsilon ball around A contains infinitely many elements of the sequence, so of Xn, then we have a subsequence which converges to this. Then there is a subsequence xnk with limit as k goes to infinity x nk equals a. This is really not difficult to see, so if we have an infinitely many, we can, from these infinitely many, if b epsilon, this crucial part here, for all epsilon, then there is such a subsequence. So the idea is really, if we can get arbitrarily close with elements of the sequence to this point A, we can then find a subsequence. We just need to pick the right order of these elements in order for it to be a subsequence. And formally, this is proven the following way. So basically, we construct such a subsequence inductively. Now, the first element is just taken x1 shall be in the ball of radius 1 around A. Just some arbitrary element. And now we proceed inductively. Assume xn1. Sorry, the first. Oops. Of course we need to get an index, and to get a subsequence we need to get a strictly increasing sequence of indices here. So assume we already have xn1 to xnk minus 1 are given in the following way, such that x and j is contained in the ball of radius 1 over j. So here we take smaller and smaller balls and then elements out of this. For all j between 1 and k minus 1. And of course the indices have to be increasing, so n1 smaller than n2 and so on, smaller than nk minus 1. If we have such a sequence, then we know that, what do I say? Then, by assumption, if we now take the index one further, so if we go to k, so we want to find an element nk, we can take the ball of radius 1 over k, and since this contains infinitely many elements, by assumption, we know that we can just choose an index big enough, because there are infinitely many, we just choose an index big enough which is bigger than this one. So then by assumption, there exists x and k in B 1 over k of A with nk bigger than nk minus 1. Sorry about the interruption, I just had a visitor in this room who was entering. It was just that confusion. So in this way I can define a sequence. And by construction, this subsequence that I have, so x nk index over k, satisfies limit k to infinity of the distance of x and k to A. Just by construction, x and k is contained in the 1 over k ball, so this is smaller than or equal to the limit as k to infinity of 1 over k, which is obviously 0. So these distances, they are non-negative, so these are now going to 0 as well by the squeezing argument here. So this means this sequence x and k, k in n, converges to A, which means we have found our subsequence and thereby proven the statement. Okay, so we can find such a subsequence in this case. Okay, this will be now needed in the proof of this theorem about sequential compactness. So let's prove the one implication of this theorem. Theorem 1167. So we want to discuss that 1 implies 2. So we will do this by contradiction. Assume 1 is true, or assume, I cannot explicitly write this down. Assume k is compact. And that we have a sequence without a convergent subsequence. That there was a sequence xn in k with no convergent subsequence. Okay, and now we argue by contraposition with this lemma 1168 here. So we've seen if for some point every epsilon neighborhood contains infinitely many, then there is a convergent subsequence. But now if A is some arbitrary point in K, then this means we don't have such a convergent subsequence. But then here, by contraposition, we also can't have that this here holds, that every epsilon neighborhood contains infinitely many. So this theorem means there must be some epsilon neighborhood for which only contains finitely many elements of the sequence, so which cannot contain infinitely many. So by lemma 1168, for all or for each A in K, there exists some epsilon, which of course depends on A, so we'll put this A in here as an index, epsilon A bigger than 0, such that B epsilon A around A contains only finitely many elements, finitely many of the sequence of the xn. Okay? Now we can use the compactness, because now we can construct an open cover. Namely, if we take all open sets of these forms, these are all open balls, so they are all open. B epsilon A of A, and now this cover is indexed by all A and K. This is some bit awkward looking, but it's a family of open sets which obviously covers K, because every element is contained in at least one ball. So because there's always a ball centered at this point included in there. So this is an open cover. Cover of K. So since K is compact, it has a finite subcover. So there exists only some A1 to AM in K, such that K is a subset of the finite union from 1 to M, B epsilon AI, triple indices. Yeah, sorry. I hope this is okay. B epsilon AI around AI, but they can only, each of them only contains finitely many elements of the sequence, and these are only finitely many sets. So this means K contains only finitely many elements of the sequence. But this makes no sense. Many of the xn. This is a contradiction, as this is a this is a sequence in K by assumption, so they all lie in K. So especially it cannot be finitely many. So this means this implies xn n in n has a convergent subsequence. Oops, so here it's not very precise. So this here is the contradiction at this point here, and from this contradiction we get this, which completes the proof of this implication. Okay, as I said, for the other implication, please consider the lecture notes. The details are all in there. It's a bit lengthy, but it's still doable, but it's just very technical, and I recommend you to study this. So this proof is in the lecture notes, and let's keep it at that. Okay, so this is now good news, because now we have a characterization of compact subsets, which is a bit easier to grasp, because this is sequences, subsequences, we can handle that. And we will now, first of all, use this new description of compactness to derive some other properties of compact sets, because this now gives rise to some descriptions or some properties that we introduced in the previous section about this, open closed sets and so on. And now we can take some of them and see that compact subsets always have these properties. So let's collect this. First of all, one notion I have to include, because I think I forgot to put this in the previous section. Namely, if we have a metric space. So in the beginning, I had said that subsets of C are compact if they are closed and bounded. But for general metric spaces, I haven't defined boundedness yet, although you might have an idea what it means. Namely, so we take an arbitrary set. A subset of X is bounded if we can fit it into a ball. Namely, if there exists some x0 in X and some r bigger than 0, such that A fits within the ball of radius r around x0. Some people define this with closed balls as well, which is completely equivalent, but we can fit the set within the ball. It's a bit like bounded sequences, so this really, if you take the set consisting of all elements of a sequence, the sequence is bounded if and only if that set is bounded, which I won't prove here, but these definitions are compatible to one another. Okay, so this is boundedness, and the theorem I'm now going to discuss is the following. Assume we have an arbitrary metric space and a compact subset. So X be a metric space, A be compact in X. Then, sorry, tiny mistake. It follows then for each compact subset that every subset, compact subset A is closed and bounded. Okay, so this is basically one, if we had characterized compactness by closeness and boundedness before, so here at least we can see compact set is closed and bounded, but in general metric spaces the converse is just false. So there are sets which are closed and bounded but not compact, and we will see one of these later on. To prove this, let me erase, and then I will discuss this with you, and we will further investigate compactness, and I hope that these proofs should also be halfway insightful and you should get a better idea what's going on. Let me erase.